Hi, in this video, I'm going to start off by looking at a simple example of the complex exponential Fourier series representation of periodic signals. So consider a periodic signal x of t with period t naught equals 1 or omega naught equals 2 pi that can be expressed in the form of the complex exponential Fourier series expansion as x of t equals the sum from n equals minus 3 to 3 of Cn e to the power j 2 pi n t, where C naught equals 1, C1 equals C minus 1 equals 1/4, C2 equals C minus 2 equals 1/2, and C3 equals C minus 3 equals 1/3, and all the rest of the Fourier coefficients are 0. So using the complex exponential Fourier series expansion, we can rewrite x of t as C minus 3 e to the minus j6 pi t plus C minus 2 e to the minus j4 pi t plus C minus 1 e to the minus j2 pi t plus C0 plus C1 e to the j2 pi t plus C2 e to the j4 pi t plus C3 e to the j6 pi t. Now, if I collect each of the harmonic components which have the same fundamental frequency and use the fact that both harmonic components for n equals 1 and minus 1, 2 and minus 2, and 3 and minus 3 are the same, then this gives us 1 plus 1/4 e to the j2 pi t plus e to the minus j2 pi t plus 1/2, which is C2, times e to the j4 pi t plus e to the minus j4 pi t plus 1/3, which is C3, times e to the j6 pi t plus e to the minus j6 pi t. And then using Euler's identity, e to the j theta plus e to the minus j theta equals 2 times cosine of theta, we get x of t equals 1 plus 2 times 1/4, which is 1/2 cosine of 2 pi t, plus 2 times 1/2, which is 1 cosine of 4 pi t, plus 2 times 1/3, which is 2/3 cosine of 6 pi t. And so this is the time domain expression for x of t given these Fourier series coefficients. Now let's take a look graphically at how this signal x of t is built up as a linear combination of harmonically related sinusoidal signals. So here's the DC component. As you can see, the DC component has a value of 1. If we add the fundamental harmonic, we get a single sinusoid shifted by the DC component. Here's when we add the second harmonic. And lastly, if we add the third harmonic, we get out the total signal x of t built from its 0th, 1st, 2nd, and 3rd harmonic components. Now it turns out that this equation here, x of t equals 1 plus 1/2 cosine 2 pi t plus dot dot, is an example of an alternative form for the Fourier series of real periodic signals. So if we suppose that x of t is a real continuous time periodic signal and can be represented using the complex exponential representation of the Fourier series, then x of t equals the sum from n equals minus infinity to plus infinity of Cn e to the j n omega naught t. This is the same thing as saying the sum from n equals minus infinity to infinity of Cn e to the j n omega naught t, the whole thing conjugate, which equals the sum from n equals minus infinity to plus infinity of Cn conjugate e to the minus j n omega naught t. Now, if we replace n by minus n in this summation, we get the sum from n equals minus infinity to infinity of C minus n conjugate times e to the power minus j times minus n, which is j n omega naught t. And if we compare this with the original complex exponential representation of the Fourier series, we see that e to the j n omega naught t is the same, so Cn has to equal C minus n conjugate. Well, also, if we take the conjugate of both sides, we have Cn conjugate equals C minus n. And this tells us that the magnitude of C minus n equals the magnitude of Cn conjugate, which is Cn. So magnitude of Cn is an even function of n for a real signal x of t. And the angle of C minus n equals the angle of Cn conjugate, which is minus the angle of Cn. So the angle of Cn is an odd function of n for a real signal x of t. And this here is known as conjugate symmetry. And this was exactly the case in the previous example, where the coefficients Cn were in fact real, so the phase was 0, and Cn was equal to C minus n. Okay, so back to the Fourier series expansion. To derive the alternative form of the Fourier series, we can first rearrange the original complex exponential Fourier series representation. So x of t equals the sum from n equals minus infinity to infinity of Cn e to the jn omega naught t, which I can rewrite as C0 plus the sum from n equals 1 to plus infinity of Cn e to the jn omega naught t plus C minus n e to the minus jn omega naught t. Now substituting Cn conjugate for C minus n, since x of t is real, we get x of t equals C naught plus the sum from n equals 1 to infinity of Cn e to the jn omega naught t plus Cn conjugate times e to the minus jn omega naught t. Notice that these two terms here inside the summation are complex conjugates of each other. So using the general identity that z plus z conjugate equals 2 times the real part of z, where z is a complex quantity, we can rewrite this as C naught plus the sum from n equals 1 to infinity of 2 times the real part of Cn e to the jn omega naught t. If I now express Cn in polar form as magnitude of Cn e to the j angle of Cn, then x of t equals C naught plus the sum from n equals 1 to plus infinity of 2 times the real part of magnitude of Cn e to the j n omega naught t plus angle of Cn, and 2 times the real part of magnitude of Cn e to the j n omega naught t plus angle of Cn equals 2 times the magnitude of Cn times cosine of n omega naught t plus angle of Cn, which means that our entire Fourier series expansion becomes x of t equals C naught plus 2 times the sum from n equals 1 to plus infinity of magnitude of Cn cosine of n omega naught t plus theta n, where theta n is defined as the angle of Cn. And this here is known as the amplitude phase representation of the Fourier series. So any real continuous time periodic signal that has a complex exponential Fourier series representation can be represented using the amplitude phase representation of the Fourier series, which, as you can see, only contains cosines of harmonic frequencies omega naught, 2 omega naught, 3 omega naught, all the way to infinity. Now, just to note here, C naught is the DC component of the complex exponential Fourier series representation, which evaluates to C naught equals 1 over T naught times the integral from 0 to T naught of x of t times e to the minus j0 omega naught t dt, which is simply 1 over T naught times the integral from 0 to T naught of x of t dt. This C naught here is simply the average value of x of t over one period. All right, now another commonly encountered form for the Fourier series of real periodic signals that are continuous in time is, if we go back to this step here, instead of writing Cn in polar form, we'll write Cn in rectangular form. So Cn is the real part of Cn plus j times the imaginary part of Cn. And this would give us x of t equals C naught plus the sum from n equals 1 to infinity of 2 times the real part of Cn plus j times the imaginary part of Cn times cosine of n omega naught t plus j sine of n omega naught t, which equals C naught plus the sum from n equals 1 to infinity of 2 times the real part of Cn cosine of n omega naught t minus the imaginary part of Cn times sine of n omega naught t. And if we let an equals 2 times the real part of Cn and bn equals minus 2 times the imaginary part of Cn, then the Fourier series expansion becomes x of t equals a naught plus the sum from n equals 1 to infinity of an cosine of n omega naught t plus bn times sine of n omega naught t, where a naught is the same thing as c naught. So what we just did is represent a real periodic continuous time signal x of t by a weighted sum of harmonically related sine and cosine function, and this is what's known as the trigonometric Fourier series, also called the sine-cosine representation of the Fourier series. Now I'm going to write out each of the coefficients a naught, an, and bn for the sine-cosine representation of the Fourier series. So a naught equals c naught, which if you recall was the average value of x of t over one period. An equals 2 times the real part of Cn, which equals 2 times the real part of 1 over t naught, the integral from 0 to t naught of x of t e to the minus j n omega naught t dt. And if we move the real part inside the integral, this equals 2 over t naught times the integral from 0 to t naught. X of t is a real quantity. X of t times the real part of e to the power minus j n omega naught t times dt. And since e to the minus j n omega naught t is cosine of n omega naught t minus j sine of n omega naught t by Euler's identity, these coefficients an evaluate to an equals 2 over t naught times the integral from 0 to t naught of x of t cosine of n omega naught t dt. And we can do the same thing for the bn coefficients. Bn equals minus 2 times the imaginary part of Cn. And if we follow these same steps here, except we're taking the imaginary part of e to the minus j n omega naught t instead of the real part, what you end up with is 2 over t naught times the integral over one period from 0 to t naught of x of t times sine of n omega naught t dt. So let me summarize what we've gone through so far. We have three Fourier series representations for a real valued continuous time periodic function x of t: the exponential representation, the sine-cosine representation, and the amplitude phase representation. For the exponential representation, x of t is the sum from minus infinity to infinity of Cn e to j n omega naught t. We have Cn equals magnitude of Cn e to j theta n. This is a polar form of Cn, and we have conjugate symmetry. For the sine-cosine representation, x of t can be written as a naught plus the sum from n equals 1 to infinity of an cosine of n omega naught t plus bn times sine of n omega naught t. Lastly, for the amplitude phase representation, we have x of t equals c naught plus the sum from n equals 1 to infinity of magnitude of Cn times cosine of n omega naught t plus angle of Cn. And here I've written out the expressions for Cn, c naught, magnitude of Cn, and the phase angle of Cn in terms of the sine-cosine coefficients an and bn. This table right here is all you need in order to convert between any of the three different representations of the Fourier series. And in the next video, I'm going to go through various examples and illustrates each of these different Fourier series representations.